This is a new chapter, chapter 10 in the book, guys. It's divided into two parts. Later on I'm going to show which parts that we are going to cover from chapter 10 and which parts you're going to cover in CMP 220, the next programming course. So we're going to study pointers and we're going to study dynamic arrays. Until now we introduced static arrays. So know how to create static arrays. Static array means that the size has to be defined before runtime. But eventually what we are going to arrive to in this chapter is how to create a dynamic array. And the dynamic array simply means that after you run the program, you ask the user what's the size of the array and then you create the array. Okay, so now you can read in the size of the array. So this is called the dynamic array. But why are they called static and dynamic? It's simple terminology. Static, it means anything that happens before runtime, and dynamic, it means anything that happens during runtime. So static before runtime, the size is already defined, and dynamic, it means during runtime. Okay, so this is what's meant by static and dynamic in programming. Okay, at the beginning of the semester, if you remember, we mentioned that the memory is a sequence of bits, right? Did you say sequence of bits or sequence of bytes? So the sequence of bytes, right? Okay, so the memory is a sequence of bytes, and we mentioned that each byte has a unique address, right? This address is called a pointer as well. So a pointer is just simply a memory address. So we can take this memory address and store it inside the variable. If you take a memory address and store it inside the variable, that variable will be known as a pointer. So this is what a pointer is. It's just simply a memory address. We have already been using memory addresses but without knowing it, and today we're going to look at the details of this. We've used the call by reference, right? And you know in the call by reference that when you pass a variable by reference to a function, then any modification you do to that variable will also be visible to the caller. Okay? What you have been actually passing is not the variable itself, but its memory address. This is what's happening with references, and today we're going to hopefully by the end of the lecture, we're going to understand what's the meaning of this. So it's a type. Pointer is a type, just like integer is a type and double is a type. Pointer is also a type. And the way to declare a pointer is using this declaration over here. So you read this declaration from right to left, and what you say, you have a variable identifier which is p, and it points to a double. You can also read it as P holds the memory address of a double. But which double? We don't know yet. It will be defined later on. So let's read it again. P holds the memory address of a double. Which double? We don't know. You can also read it as P is a pointer to a double. So whether you say pointer, it's an address, or it's the same thing. So now we understand that pointer is just simply a memory address. So this is a pointer to a double, or it's an address of a double. Okay. So this is saying that the pointer itself is not a type as such, but it holds the address of a type. So it can hold the address of an integer, it can hold the address of a double, it can hold the address of float, and so forth. Okay. So it's just simply the star over here, and you can declare pointers and non-pointers in the same line if you wish to. Although it's not a must, because if you have a semicolon over here, then we can start a new declaration over here. So you can have those two over either declared in 4 lines of code, or you can declare them as you wish. But this says that P1 holds the address of an integer, P2 holds the address of an integer, V1 is an integer, it's not a pointer, V2 is an integer, it's not a pointer. Okay. So the pointer is just simply an address. The address is an integer. Now, although the address is an integer, guys, we cannot deal with pointers as if they are numbers. We cannot deal with pointers as if they are numbers. Numbers, we can divide them, right? We cannot divide pointers. But later on we're going to see that there's something called pointer arithmetic. Now with pointer arithmetic, what we can do, we can say pointer plus plus, pointer minus minus. We can do simple things with pointers, but we cannot deal with them as if they are numbers. Okay, so the pointer arithmetic is different than the regular arithmetic that we are familiar with, and we're going to come to that later on. So although the pointer is an address, the address is an integer, yet we cannot deal with pointers as if we are dealing with numbers. This is the point. So now pointing to, what does it mean? If you have P1 and it holds the address of an integer, V1 is a pointer? No, it's not, it's just an integer. V2 is also an integer. Now what you can do, you can make P1 point to V1. Now the AND over here, it means give me the address of. Give me the address of V1 and store it inside P1. When you take the address of V1 and you store it inside P1, now we say that P1 points to V1, because P1 has the memory address of V1. Okay? So if you want to illustrate that, it's just simple illustration. So let's assume that there is the memory address, and then there is the variable itself. So the memory address, for instance, was 10, and the variable is V1. Somewhere else outside the memory, we don't know where, so we can say that there are other addresses over here, and then there is some other address, and we have P1, right? And then what we said, that P1 is equal to the address of V1, right? So essentially what we're saying is that P1 is equal to 1, 1. Did you get it? So P1 is equal to the address of V1, which means that we are going to store 101 inside P1, because P1, it's an address of V1. What's the address of V1? 101. So 101 is stored inside P1. So this is the interpretation of this operation over here. P1 is equal to the address of, this is how you read the @ sign, the address of V1. Give me the address of V1 and store it inside P1. So now we have the address of V1 and it's stored inside P1. So how can we make use of this? We don't know yet. Eventually we will be able to store to V1 and read from V1 through the pointer, which is P1. Okay? But we don't know how to do this yet. So what we know how to do up to this point is how to declare P1 and how to get the address of something else. Okay. Nothing, it will remain the same. And we did not change the address of P1, right? So what's the problem? We did not even change the address of V1. So there's the addresses, they remain the same. The only thing that we did over here is that we took the address of V1 and we stored it inside P1. We did not do anything else. Okay, back to the slides. So this is the address of operator, and now P1 holds the address of V1. Okay. Now you can print out the value of V1, and you can also print out the value of V1 through P1. We know how to print out V1, so this is business as usual over here. But surprisingly, we can also print out the value of V1 through the pointer. Now this operation over here, we did not see this before. This is called a dereference operator. A dereference operator, it says, don't print out the address, which is P1, Because if we print out P1 in this example, let's go back to this simple example. If we print out C1 over here, P1, what will be printed out? Say again? 101. The value of P1 is 101, right? So if we print out P1, what will be printed out is 101. However, let's assume that the value of V1 was 20 over here. Now, we can access the value of V1 through the address itself. So we can say cout dereference P1. Dereference P1, guys, it means I'm not interested in the address, I'm interested in the content of the address. What's the content of the address 101? 20. So 20 will be printed out. This operation is called give me the address of, and this operation is called dereference. I'm not interested in the address, I'm interested in the content. Okay? So you can think of the address as a key if you wish. And if you can think of the dereference as the content of that locker. If you're opening a locker with the key, then dereferencing is the content and the address itself is the key. So in this case, what you're printing out is the value of the key, the value of the address. And in this case, what you're printing out is the content. Okay? So can we do other things to it? Yeah. So using the same logic, you can read in P1. So let's assume that the user over here entered 30, followed by \n. What do you think will happen? Now let me ask you those two questions. Question number 1. What will P1 contain? And question number 2, what will V1 contain? Yeah, let's start with the first question. After this operation, so we read dereferenced P1. What's the value of P1? The value of P1 did not change because the value of P1 is the address of V1. What's the value of V1? 30. It used to be 20 and now it's 30. So we can access the content of V1 through the pointer if we use this dereference operation. Okay, so now again, just to summarize, we have the address of operator and we have the dereference operator. So we have the address and we have the content of the address. Okay, so this is called the dereference operator. Again, so now here's a full example. So V1 is equal to 0. Who would like to read this line? How does it read? P1? P1 equal to address of V1. Excellent. P1 is equal to the address of V1. What do you think is happening over here? No. The one answer is P1 is pointing to the address of 42. No. Yes. Now when you say dereference P1, you can just replace this with V1. V1 and the dereference P1 are exactly the same. So this is as if exactly we're saying V1 is equal to 42. Okay, so when you dereference an address and you say dereference address is equal to 42, it's exactly as if we are saying V1 is equal to 42. Okay, so now 42, where is it stored? Inside V1. So when we print out V1 at this point, we're printing out 42, and when we print out dereference P1, what will we print out? 42 as well, because dereference is V1. So the answer is 42 and 42. Right. Now this is the address of operator. And what we did previously, we used it in functions. Just refresh your memory, although you know this because you've revised your midterm. But anyway, so let's assume that you have a void function. And it has an integer I. So now we understand that this is the address of I. right? So the AND operator is the address of I. Right. If we have the address of I, well, pay attention to this. If we have the address of I, then logically, if I want to access the content of I, what do I do? Star I, right? Right. Let's call this P such that you don't get confused. And let's try this again. So let's assuming that you have a variable called P and you're passing it by reference to a function. Fine. If you want to print out the content of the address, from what we have learned, this is what we should do, right? Because this will dereference P. However, this is not the case in functions. What will happen in functions is that the reference will automatically be dereferenced. And I cannot emphasize this enough. So what will happen is that this is correct. Let me repeat this statement. When you pass a variable by reference to a function, it will automatically be dereferenced. You don't need to dereference it. It's a syntax simplification. طيب. Now, it's a contradiction as well, so it's not consistent, it's inconsistent, because we know from pointers that what you are passing over here, you're not passing the variable P, you're passing the address of P. But if I have the address of P, then I cannot print it out this way, right? Because this will print out the address. But I'm not interested in the address, I'm interested in the content. How do I print out the content? I have to dereference. So what I have to actually do, if C++ was a consistent language, then this is what I should be doing. However, they decided in C++ that let's simplify this, and if you pass a variable by reference to a function, then it will automatically be dereferenced. Did you get it? It's a simplification. Okay, so we have used this in the call by reference. What we pass, we're actually passing the address of, we're not passing the actual variable. And this is why any modifications that we do to it will be visible from the caller, from main. However, it's automatically dereferenced, so we don't have to worry about dereferencing. Okay, can we assign one pointer to another? Yes, we can, and there are two separate issues that we have to be aware of. So let's go back to our example over here. So we have P1 is equal to V1. Let's also have another variable, say at 105 for instance. And we have another variable called V2, and the value of it is 40. And we have another pointer, 1005 for instance, and it's P2. Okay. Right. So if I say P2 is equal to P1, then the question is, what's the value of P2 at this point? What's the value of P2 at this point? Just a minute. Who said 1001? It would be 1001 if we did this, right? If I told you, give me the address of P1, what will the answer be? It will be 1001. I did not ask for the value, for the address of P1. Okay? We just simply asked for the content of P1, and the content of P1 is, what's the content of P1? The content of P1 is the address of V1. The address of V1 is, so what's the value of P2 over here? It's 101. So we can assign a pointer to a pointer, yes. Okay. Now, let's take another scenario. The second scenario says that P2 is equal to the address of V2. So at this point, guys, what's the content of P2? 105, the address of P2. Fine. Now later on we came and said that P2, let's dereference P2 is equal to dereference P1. What happened now? Sorry? 20? Stored where? In V2. And we agreed that this is exactly as if you're saying that V2 is equal to V1. So now whether you say dereference P2 or you say V2, or whether you say dereference V1 or P1 or V1, those are the same. So it would be as if you are assigning V1 to V2, which means that now the value of V2 is 20, right? So V2 is equal to 20, and the value of V1 is also 20. So now both of them are equal to 20. So we can assign pointers, and we can also assign the values over here. The value pointed to by P1 to the value pointed to by P2, which is V1 and V2. Okay, this is an illustration, so let's try to figure out what's happened over here. So there is P1 and P2, and the content was 8 and 9. Where did 8 and 9 come from? Is there an example of 8 and 9? Or is this a new example? Seems to be a new example. So when you're assigning the content, both of them will have the same content? No. So this is P1 is equal to P2, this is something else. We're assigning the address of P2, we're assigning to what's stored inside P2 inside P1. So P1 used to hold the address of 8, and P2 used to hold the address of 9. After we assign those two, now both of them are referring to the same address. And this is what we did over here. At this point, both of them are referring to the same address. Right? I think the illustration we did over here is a bit more clear than the illustration in the slide, so I'm just going to stick to this. So what you have in the slide over here is just a repetition of what we did with this simple illustration, so I don't want to confuse you with it. Of course, you can have a look at it on your own time. Okay, before we introduce the new operator, let's write the full program now, trace the program, look at the addresses, and make sure that you understand it before we move on. So we don't need this now, and let's write a full program to illustrate the concepts that we have introduced. So hash include IOStream, is the font okay, guys? Okay. Void main. So we use double pointer 1, star pointer 1, star pointer 2, V1, V2. In terms of syntax, you can have the star next to P1. You can have a space, that's fine. You can have the star next to double, that's also fine. So it's flexible. Okay. Typically, a good approach is just to have the star with the variable itself, although it doesn't make a difference. Okay. So all of those are a bit flexible. So let's have V1 is equal to 20, and V2 equals to 40. And then let's start with the following. Let's say that P1 is equal to the address of V1 to the address of V2. Okay? And let's have a breakpoint over here. We didn't do anything yet, right? So what's happening over here? What will happen after we execute this line of code? The address of V1 will be stored inside P1. Okay. Okay, so what we did over here, we took the address of V1 and we stored it inside P1. So we don't know what the actual content is. Let's debug the program. Start debugging. Okay. V1 is equal to 20, can you see it? And V2 is equal to 40. Now look at P1. And the type of P1 over here, it says clearly that it's an address of a double, and this is what the address is. And this number is in hexadecimal. We agreed that in hexadecimal, if you didn't do digital systems yet, the count is from 0 to 15, and it contains 0 to 9, and then A, B, C, D, E, F. Okay, so this is the address in hexadecimal, but this is the actual memory address of V1. If you dereference P1 over here in this small window, it means that you just click on the plus. Can you see the 20? The 20 is the dereference of this memory address. And if you dereference P2, P2 is not assigned yet because we did not move on, right? So P2 is not assigned yet, and the address is just null. Okay, the address is 0. 0 is called null because we did not assign it yet. So let's assign it. Now P2 is assigned, so this is the new memory address. It's the memory address of V2, right? And the value of V2 is 40. So if you expand this, if you dereference it, what it's pointing to is actually the content is 40. Fine? Okay. What else did we do? We also assigned, we said that P1 is equal to P2, right? So let's see what will happen at this point. Start debugging. Now, P1 and P2, they have the addresses of V1 and V2, right? Those are different addresses. So this one ends with 10 and this one ends with 00. Can you see them? And at this point, we're going to assign what's stored inside P2 into P1. The what's stored inside P2 is this number, and we're going to assign it to P1. So what will happen is the following. Now this address ends up with 800, and this address ends up with 800. Can you see it? So we assigned an address to P1. Now both of them, they have the address of V2, right? So the value of V2 is 40. Let's double check. This is 40, and this is 40. Okay. So the pointer is flexible enough to point at different variables, V1 or V2 or V3 during the program. You can change it. We did one last thing, which is the dereferencing. So now instead of this, let's do it this way. So what will happen now? This is exactly as if you are saying V1 is equal to V2. So now the value of V1 will change. Both of them will become 40. But the address which is stored inside P1 and the address which is stored inside P2, they will remain unchanged. Let's see that. Start debugging. So now those are two different addresses, P1 and P2. Both of them, they hold the address of V1 and V2. Of course, when you run this program different times, V1 and V2 will be in different locations inside the memory. Of course, okay, it depends on the content of the memory. You don't specify this. C++ and the operating system is doing it on our behalf. So V1 and V2 are stored inside the memory, where we don't know until you run the program. So now we know that this is the address of V1 inside the memory, and this is the address of V2 inside the memory. Okay. But now at this point, we're going to, as if you're saying V1 is equal to V2. So both of them are 40, right? So v1 is equal to v2. The addresses are untouched. We did not change the addresses. We just changed the content. So what we know until this point is we know how to declare pointers, we know how to get the address of, and we know how to dereference. Okay? We know how to assign a pointer to a pointer, and we know how to assign a value to the content of a pointer, just like in this example when we dereference. Okay? Any questions before we move on? I never tried it. I think it's a syntax error. It doesn't. It's a syntax error. Logically, yeah, I can see your point, but it's a syntax error. Does it work? C++. Mesa.
Here, the content of you want to change, right? You can't float it. And the other case, the access change and the content event, like the time floating.
So this is the other case you're talking about. In this case, we're assigning, this is as if, exactly, as if we are saying v1 is equal to v2. Okay? In this case, it's exactly as if we are saying that p1 equals to the address of v2. Because what p2 is the address of v2, right? p2, it's the address of v2. So this line of code, it's exactly as if you are saying that p1 is equal to the address of v2. And when you dereference, it's exactly as if you are saying v1 is equal to v2. I think it's more clear now when we wrote it this way. Yes? No. No. The address of v1 was stored inside p1, but we did not change the address of v1. You cannot change the address of v1 because v1 is not a pointer. What we changed over here, we changed the value of p1, but we did not change the value of the address of v1. This remains as is. Other questions? Okay, the new operator. What we can do is something like this. I'll come back to this slide in a minute. So let's have an integer star ptr. This is a pointer. It's a pointer to an integer, right? It holds the address of an integer. Which integer? Do we know yet? But what we can do is the following. We can say that ptr is equal to new. This is a new keyword. We did not see it yet. Notice that it's in blue, which means that it's a part of the C++ dictionary. It's a C++ keyword. It's equal to new integer. Now we have created a new integer. Two things happened. A new integer is created, and the address of that new integer is stored inside ptr. But what's the name of this new integer that we just created? Does not have a name. It's a nameless integer. We created a nameless integer. We took its address and we stored it inside ptr. Let me repeat that. We created a new integer. Does not have a name. It does not have a name. And we stored the address of the new integer inside ptr. I'll answer that in a minute. If you go to Sahara Center, the first floor, there is a abaya store called Bidun Ism. Do you know it? Yeah. Bidun Ism, it means nameless. There's a store called Nameless. Did you see it, guys? Maybe you're not interested in abaya, but there's a store there. And this variable, it's also Bidun Ism. It's also a nameless variable. We took its address and we stored it inside ptr. Your question is, if we have an integer that does not have a name, how can we assign values to it? This is your question, right? The what?
The element is not.
Yes.
It's for the value, not for the address.
Okay. So now if you want to store a value to it, you can just simply dereference PTR and say PTR is equal to 12. We have stored the 12 inside the nameless integer. So can we access this nameless integer? We can only access it through the address. So what's the address? PTR. So can we print it out? Yes, you can. Come on. PTR. You can create a nameless variable and access it through the address only. Let's recap. So the new operator over here did two things. What were they? Two things. What are they? It created a nameless variable and took its address and stored it inside. So the new operator, you can, if you want to think of it as a function that returns a value, then it returns the address of the variable that it has created, and this address is stored inside PTR. Now this is called dynamic memory allocation. It's dynamic because it happened during runtime. Before runtime, this nameless variable integer, it wasn't created yet. We created it during the run of the program, so it's a dynamic variable. PTR, it's not a dynamic variable, because during the compile time, the compiler, it knows that there is a variable called PTR. And the size of that PTR, by the way, the size of the address is 4 bytes, the integer, okay, because the address is represented as an integer, it's 4 bytes. 1632. Would it be different on systems that are 64 bits? It might be different. Okay. So let's assume that the address is 4 bytes. During the compile time, the compiler knows that there is a variable called PTR, but there is no such variable. We did not create this variable yet. It was created during runtime. As opposed to, if we have an integer I, this is created during compile time. The compiler knows that there's a variable called I, and it has to consume 4 bytes, and those 4 bytes are reserved during compile time. Now, whereas if you do the dynamic variable over here, you create the integer during the runtime. If you create the integer during runtime, it's no longer called a static variable, it's called a dynamic variable. So this is called a dynamic memory allocation. Dynamic because it happens during runtime. Memory allocation because you're allocating 4 bytes to the nameless integer. Let's go back to this slide. So the new operator, since pointers can refer to variables, type can dynamically allocate variables. This is what's happening. Dynamically, it means during runtime. Allocate variables, it means that we're going to allocate 4 bytes to a nameless integer. Okay? You can allocate 1 byte to a nameless character as well. So we can use the new operator, and this is how it works. So P1 is equal to a new integer. So this creates the nameless variable, and it takes its pointer and its address, and it stores it to P1. So two things are happening. Create a nameless integer, take its address, and store it to P1. Fine? Okay, I think this example is very similar to what we have did, to what we have done. And this is an illustration. One last point, but we're running out of time. One last point is when you create the new integer, it's an optional to give it an initial value. So in this case, we don't need to give it this initial value. Okay, this is optional. So just like you can say that you have an integer I and the initial value is 20. You can also do a similar thing with the dynamic memory allocation. Okay. So again, whether you do that or not, this is optional because we can always write it the explicit way, and this way is more flexible because you might want to change it later on, of course. But can we read this from the user? By all means. So you can also see in star PTR, which is our nameless variable. Now the new operator, guys, this will be our entry point to dynamic arrays. So now we know how to create one dynamic variable, but can we create a list of dynamic variables? If we create a list of dynamic variables, then we have an array, right? So eventually you're going to arrive to that. Yes?
What about if you say that the pointer is equal to 12 but the number is 5?
Right. This is your question, right? What will happen if we assign a 12 to PTR? Right. Now PTR is a memory address, right? So what you're trying to do, now let's assume that you created this nameless integer and the address of that nameless integer was 101. So now what we have is that PTR is equal to the address of the nameless integer. Fine? At this line of code, what you're trying to say, you're saying, look, I'm going just to trash that old variable, I'm going to totally ignore it, and I'm going to point somewhere else. So now PTR is no longer pointing to the nameless integer, it's pointing somewhere else. But where somewhere else we don't know. What's the content of the memory address 12 we don't know. Okay? So this is not a wise thing to do. It would be okay if you take, for instance, the address of I, then that's fine. Right? This is perfectly acceptable. You say, well, PTR, I don't need this nameless variable anymore, and I'm going to take the address of I instead. Then that's fine. Okay? But I think we have to stop here. Do you have any other questions?